I'll be starting in, looks like 2 minutes. For those of you, I know a lot of people like to have a copy of the slides. You can scan the QR code up here, and that'll take you to the slides. And my website, wirewrapodyssey.com, is on this QR code and has way more information than I'm going to be able to give you in the next 30 to 45 minutes. So feel free to peruse there. I've got my GitHub repository here, and the only social media that I'm on is Reddit. So if you happen to see Skaven81 posting in the vintage computing subreddit or the electronics subreddit or the astronomy subreddit or something, that's me. Let's get started. So, hi, my name is Paul Krizak. I really have no credentials to be up here, so I'm going to try to explain who I am and why I am authorized to give this talk to fine people. This is me in 1994 when I was 13 years old, and you can see here this is my 5150 that I had just gotten for Christmas. You might note that 1994 is not when the 5150 came out. That's because it was like 7 or 8 years old. It was a used computer when I got it. But that's what kicked off me having my own computer. And so I am well aware of vintage computing stuff because I started when I was about 13 with secondhand gear using all PC stuff. I didn't get into the Commodore and the Amiga stuff, sadly. But I had an 8086, or 8088 rather, a 386, 486, K5s, K6s, Thunderbirds, all sorts of stuff up until modern day. In college, I worked at AMD. This is me at AMD helping ensure that the dual-core Opteron got taped out. So that was a fun internship. And I ended up working at AMD as in IT. So I'm not an electrical engineer. I'm just a computer scientist, really a sysadmin. And also in college, I took an elective where I got to build some stuff on prototyping boards, and so I got to learn how to stitch digital chips together and make circuits work and stuff. So I got a little bit of background in college, but mostly these courses, I took a few electives in college that inspired me that I could build a computer myself from scratch. And so in 2010, I managed to get a hold of this logic analyzer, which you can see at my booth, and I'll be doing a demo of that logic analyzer at 2 o'clock. And you can see I started prototyping some stuff. I think I can do this. I think I might be able to build some stuff. So that's where the journey started, the Odyssey, if you will. I will quickly correct folks who think that the Wire Wrap Odyssey is like a wire wrap version of the Magnavox Odyssey. It is not. It's a completely different thing. I even thought when I gave it the name, are people going to get confused that it's that? No one remembers the Magnavox Odyssey. Of course, all of you remember the Magnavox Odyssey. So yeah, it's not a Magnavox Odyssey. This is all custom from scratch. And importantly, I designed it to not be a toy. So for those of you that have watched things like Ben Eater's videos, which are amazing, some of the best learning about how to build digital circuits I've ever seen. He is amazing. But what a lot of people are doing, which is awesome, is they're taking these videos, this learning, and they're building computers on breadboards that are awesome. They're using 6502 processors or Z80 processors and doing some really cool stuff with them. A lot of folks are even doing what I did and doing TTL computers that just are their own design, but a lot of them end up being toys. And I define a toy as something that is something you can put on a shelf, and it's neat to look at, and you kind of poke at it, and maybe it can do the Fibonacci sequence, but you can't really do anything with it beyond that. I wanted to build something that was a real computer. So I wanted to make sure it had a proper address bus. It could address up to full 64K of memory. It had a proper 8-bit data bus, not like a 4-bit toy computer. I decided on a microcoded instruction set that allowed me to expand the instruction set as I needed, and I've actually had to do that a couple times to write some single instruction, multiple data type instructions. I gave it interrupts so that it can actually do things like when a byte comes in over the UART, it can interrupt the CPU. I don't have to write polling loops. I can actually have proper interrupts. And I did not want to use a VLSI CPU. So I wanted to build something that wasn't a toy without using a professional CPU, which was rather challenging, but that was the point, as I wanted to do something that was fun, challenging, and really taxed what I was capable of. The Wire Wrap Odyssey has a 16K ROM memory space. That's where program ROM, BIOS type stuff goes. 32K of RAM, about 8K of that is allocated to the video card, and then I just recently added a 1 megabyte extended memory, which is accessed through 2 4K pages. And it's got a 640 by 480 60 hertz video card. And that, I think, is the biggest thing, along with interrupts, that makes it not a toy, is that it actually can display a 60 hertz full VGA signal. It isn't pixel by pixel, it's a character display, but you can still do a lot with a 64 by 60 character display. You can use all sorts of tricky, fun stuff with the fonts to do, sprites, basically. And I'm looking forward to doing some like neat games and stuff that I can use that proper display with. And it's got a number of proper peripherals. So it's got a PS2 keyboard, a Dallas RTC, an RS-232 UART. Soon it'll have an ATA port, so you can hook up a hard drive or an SD card adapter or something. And so I feel like all of that together makes it not a toy. So this is something that I could, if I wanted to, I could set up after months and months and years of writing more software for it. I could technically sit down and use it as like a computer and actually do productivity stuff or games on it. Oh yeah, I also wrote a real mode operating system for it, so that's been a fun project as well. So with that background in mind, what we're going to talk about over the next 40 minutes or so is, first, I'm going to give you like the 5-minute version of how CPUs work. Everyone in here, I'm sure, already knows this, but I'm just going to give the high-level overview from my perspective, remembering that I'm not an electrical engineer. I took one elective in college about this, but the point is that I took that small amount of information, that knowledge, and I was still able to do this. And that's kind of the message I want to convey during this talk, is that I'll talk about kind of what you're shooting for if you're going to build your own CPU, and then talk about what I did, which doesn't mean you have to do that. People can build all sorts of crazy wild stuff. If you've got a cool idea about, oh, I wish I could do instruction sequencing like this, do it. It's freaking awesome to do that sort of stuff. But I'll talk about how I implemented the system architecture for the Odyssey, and then at the end, I'll talk about the physical construction that I used wire wrap. There are pros and cons with doing wire wrap versus PCBs versus breadboards versus point-to-point soldering, and I'll do a quick overview of those different methods and why I chose wire wrap for this particular project. So let's talk about how CPUs work, more or less. So this is kind of more like how microcontrollers work, which was more like how the old 8-bit 6502s, Z80, 8088 type processors worked. And the first part is a CPU is basically going to sit on some sort of a memory bus and have some registers. And most of what a CPU is doing in its day-to-day life is just moving data around. It's not doing magic inside. It's literally just saying, take data from memory, put data from memory into this register, take data from this register, put it in that register, take data from this register, put it back into memory. Like that's a lot of what a CPU is doing. The problem is that ROM and RAM can only read or write a single address at a time. You put an address on the address bus, and whatever's listening to the address bus, if it's in its memory range, maybe that's the RAM range or the ROM range or a peripheral range, it then puts a value from that address on the data bus. So the address and data bus are now in use, which means you can't read from memory and then write back to memory in the same operation. You have to read, store that data in a temporary register somewhere, and then if you're going to write it back, you have to then put a different address on the data bus, put the register on the data bus, and then write it back. So registers are really important because that's what gives you the ability to store values from RAM or ROM and put those values back into RAM or RAM at a different place, or to write it to a peripheral, or to modify it and then write it back. So you're going to have some registers. It's technically possible to create CPUs without registers. In fact, I think this 6502 has the concept of a 0 page or something, where it actually is mapped to memory and you can use some of the memory as registers. I didn't do that. I just actually implemented real registers in 7400 series chips and did that. So here's an example of why you need registers. So if we're going to do an LDI instruction, that's load immediate, meaning we're going to put some sort of value that's hard-coded in our program, and we're going to store that value in in memory. So to do that, we first have to, we're going to put this value into a register. So to do these sorts of instructions, like we look at the LDI instruction, you first have to go to ROM, get the value out, and then put it in the register. That's pretty easy. But if you're going to load a value, say from your program, and then put it in RAM, so like I want to put a static value in my program and I want to stuff it into a peripheral or something, which is memory mapped, well, now you need a register because you have to put something from RAM into the register, and then there are other instructions that you might have to do on those registers. So the key takeaway there is when you're thinking about that aspect of a CPU, it isn't really complicated in the sense that you don't have to create a complex architecture around your registers. You've got a memory bus, you've got a data bus, you've got some registers that are going to store temporary values, and then your instructions need to be able to read and write back and forth between those items. And that just is a matter of setting flags to output the value to the memory bus or read from the memory bus or something like that. The second thing a CPU does is the instruction sequencing. So once you're able to move data around in your CPU, you need to tell it how to become an automaton. You'd have to tell it how to go through the state machine and move through instructions. So that's most of what the rest of the CPU is doing, is just figuring out what to do next. So the instruction is busy doing one thing, and it can't just stop there. The clock needs to tick, and it needs to move on to the next thing. Well, how do you program your hardware to do that? So almost every CPU in existence has something called a program counter. This is a special register that stores the memory address of the current instruction that you're processing. And it's, in my case, it's a 16-bit value because it's a 16-bit architecture. And importantly, it can count up and it can load new data. So you can do a jump, for example, by loading a new address into that program counter, and that tells the CPU to load this next instruction at a different location, or you can just increment it to move to the next item in the program. The instruction sequencing goes by taking the data at that address that's stored in the program counter and storing it into a register, which again, almost every CPU in existence has something called an instruction register, which is you load that value out of memory. It could be 8-bit, 16-bit, 32-bit, whatever it is, however you designed your instruction set is going to get loaded into that instruction register. Then that instruction register plus the internal state of the CPU becomes the input to your control logic. And the control logic can be anything you want. An off-the-shelf CPU where they're designed using VLSI techniques will be this giant array of ANDs and OR gates and all sorts of crazy logic. I implemented mine as a lookup table in EEPROM. So you can do it lots of different ways, but the whole point is that once you have your instruction in a register, you amend that register with the internal state of the CPU, like the CPU flags, and then that generates the control signals, which takes you to the next state. And the control signals will do things like turn different chips' output enables on and off, or tells a particular chip to load data off the data bus and store it internally, or to increment, or to decrement, or to clear. Like there are all sorts of things that those control signals can do, but the net effect of those is that you move to the next instruction or to the next micro-op in your instruction. The third thing that an instruction set needs to do is basically not much more. An instruction set doesn't have to be super complicated. You look at the modern x86 instruction set, for example, and it's a tome. It's an encyclopedia of instructions, and they're ridiculous. But all that an instruction set needs to have, you need some load and store commands to get data in and out of memory. You need some stack commands, push and pop, so that you can store data on the stack and pop it later, so that enables you to do call and return. You need call and return functions, so you can call subroutines and get back. And you need some sort of math and logic with an arithmetic logic unit, so you can do add, subtract, shift, set and clear bits. You need some sort of branching commands, so depending on what the ALU did, like compare these two values. If they're equivalent, jump here. If not, jump there. So you need some sort of branching command. And if you don't want it to be a toy, in my opinion, you need interrupts. And it's important to note that each of these instruction classes depend on the one before. And that's important because it means you can actually build one of these things piece by piece. You don't have to design the whole thing all at once and implement the whole thing before you can start testing it. You can build the load store unit, test it, make sure it works, then build the stack unit, then build the call return unit, then build the next one. You don't have to build it all at once. The last piece of what CPUs do is interface with peripherals. A very common way to do that is through something called memory mapped I/O. That's basically where you take a chunk of your addressable space. In my case, it's the top 8K or so of memory. And you basically just have your peripherals listen for given addresses. So they kind of take over a particular address range. And anytime that address appears on the address bus, they wake up and they're able to either read or write data to the data bus. And that's how the CPU can communicate with them, reading and writing data just as if it was memory, but actually it's reading and writing to the peripheral. So this is very common. I think it's even how the old ISA bus worked on the old 8-bit machines. And so it's a model that is well tested and is really easy to implement. Interrupts are also surprisingly not difficult to do. The idea is that when a peripheral needs service, it can pull an interrupt line low. Depending on how you want to design your CPU, this could be multiple interrupts or a single interrupt. There's a lot of different ways to implement it, but the idea is that as the CPU is going through its logic of executing commands, it's going to reach a point where it is going to load a new opcode. It's completed its last opcode and it's ready to load a new one. At that point, it can just look at the interrupt line and say, well, if interrupt is set, then don't load the next opcode, but instead run this other command that's an interrupt command. And that interrupt command can have all the microcode in it that knows how to deal with an interrupt, saving the CPU state, saving the ALU state, branching to an interrupt handler, all that sort of stuff. So it doesn't have to be super complicated because you can actually implement it in your instruction set. You don't need a bunch of custom hardware logic to actually handle interrupts, except for the ability to pull an interrupt line low so that your instruction sequencing knows when to go to the next to the interrupt instruction instead of into the next instruction. So let's talk about how I designed the Odyssey. Done, right? All right, no, I'm going to cover this up and we're going to talk about it piece by piece because this is actually the order that I built things in. And I'm going to show you that it doesn't have to be crazy complicated. Because I decided right off that I was going to do a 16-bit address bus and an 8-bit data bus that I was going to use. With that in mind, I decided what RAM I was going to use. I decided on a dual port 32K RAM, so that's got a 15-bit address space. So I set up my memory map so that the bottom of address space, 0 to 3FFF, is ROM. So I've got 16K of ROM, then 32K of RAM, and then 16K of undefined. I just left 16K that I could use for peripherals or something like that were unmapped. But once I had that in place, I added a program counter. So I literally just wired up some counter registers that could read and write from the address and data bus, and that's my program counter. So I was able to test that. Yep, I'm able to increment, decrement. I'm able to sequence through ROM in this case. Starting at address 000, I can just keep incrementing and it'll go through. It doesn't do anything yet, but I'm able to do that. Then I added the transfer registers. So the transfer registers, actually, did I skip a step here? Oh, I did. So the instruction sequencing. So that was the other thing that I implemented here was the program counter on its own can't do much. It can increment. So I went ahead and implemented the rest of the control logic. So that was the first thing I put together. So this didn't actually do anything yet. I just tied one of these lines low so that it wouldn't do anything. But then I chose to use this mechanism where an opcode is loaded out of the data bus. It appends some flags from the ALU, which were tied low because I didn't have an ALU yet, and then a sequence counter. And that's what actually does the microcode. I don't have enough time to get into it in depth here because I'm going to run out of time. But the important thing is that I did RAM first, ROM, then I implemented the program counter and the instruction logic, and that proved that I could at least run instructions 1, 2, 3, 4. They didn't do anything yet. It was just a bunch of no ops, one after the other, but I proved that I could actually run programs in order. Then I added the transfer registers, and the transfer registers are not actually addressable by instructions. They're actually used by the microcode to store data temporarily. So as things are happening, like you're loading data from memory, you might need to get an address that you're going to be loading from memory, so you have to put that address somewhere. So that gets put into the transfer TA register, and then that data gets loaded into the TD register, and then it knows what to do with it next, maybe write it back to memory or something like that. So this is all used by microcode. And once I added the transfer registers, I could actually implement load and store operations. So with just the hardware you're seeing on the screen, I already can implement load and store instructions, which means in my case, because I already had a video card at this point, I could do hello world. I could actually print hello world at the top of my display. I could clear the screen. I could do all sorts of stuff. Of course, I didn't have any branching logic or anything, but at least I could prove that the CPU was running. It could actually move data around in memory. It could interface with the peripheral, the video card in this case, and do something. So I went ahead and added a stack pointer. And what the stack pointer does is allows you to implement a stack. This is controllable through microcode, so you can bump the stack pointer up and down. In my case, I've got a 256 byte stack. And what stacks allow you to do is call and return. So with just that, now I can implement a call function and a return function. So I can run subroutines, which is cool. So I still can't do much with as far as data goes. I can basically just branch I can call a subroutine that can maybe do something and run it in a loop, but I don't know how to stop the loop. I can just move data around, and I can put stuff in the stack. Then I added the ALU. So that's where your main registers come in. So I've got 8 registers, A, B, C, D, each that are 16-bit and split into high and low segments. And 4 of those registers can talk to the ALU, and the ALU can write back to the data bus. It turns out that was a not very good architecture. Don't copy this, but it works. And with an ALU, suddenly these flags actually mean something, which means now you can do branching instructions. Now you can say, test, subtract these 2 values. If the result is 0, then go here. Otherwise, go there. And of course, all the other stuff that an ALU can do. Now you can shift. Now you can multiply. Now you can divide. Now you can add and subtract and XOR and all the bitwise stuff. So that adds a huge amount of power. But still, all you're doing at this point is running static code. So that's when you add an interrupt handler. So at this point, that's where this comes in handy, is that had the forethought to make sure that the instruction sequencing knows how to deal with if there's an interrupt pending. Notice that I didn't have to build the interrupt handler early on. That was the last thing I built. It's arguably one of the more complicated pieces. I actually made a bunch of mistakes, and I had to go back and fix some of this earlier stuff because I messed it up. But the point is, you can build all this up in stages, and the interrupt handler can come last. And then finally, once you have an interrupt handler, once peripherals can raise an interrupt, now you can build peripherals that can do things like asynchronous communication with the CPU. And that's when I added the keyboard controller, the RTC and timer, and the extended memory. So everything I talked about here with the Odyssey is all designed on 7400 series logic. I'm going to give you a quick primer here because I'm sure a lot of folks, I didn't know this going in, and so I made a bunch of mistakes when I was prototyping initially, and I wish someone had taught me this. There are many series of 7400 series chips. There's S, everyone's heard of LS, and so newbies like me would go out and say, oh, well, clearly LS is what I want. Everyone's doing 7400 LS series. Well, LS is old school. That stuff's, you have all sorts of weird voltage problems, and you can't chain many of them together because it's old Schottky stuff. So then there was the C series, which is the old original CMOS, and then there's high-speed CMOS, which is still horrifically slow by today's standards, but it's the CMOS, and what CMOS is really good at is that when a signal is high, 5 volts. When it's low, 0 volts. It's a very sharp, nice square wave. With LSTTL, it's not. You get these really slow ramps, and they only go up to 4 point something volts, and you chain them together, and they only go 3.7 volts, and it's a pain. So if you're gonna build something like this from scratch, I recommend the HC series. These chips are commonly available. That's why I chose the series. It's not the best overall, but they're available. You can get them on Jameco, you can get them on Mauser, you can get them on Arrow. They're all over the place, and they're easier to work with than the LS series. If you need something that's faster than the HC series, there's also the A and the F series, which have their own issues with voltage levels and stuff, but their propagation times are way lower. So for things like address decoding, you might want to use an A series or F series chip. Everything else in the Odyssey is just made of logic gates. and or not XOR. Some of the slightly VLSI type stuff would be things like multiplexers, demultiplexers. You take 2 control signals and turn them into 4 outputs that might go to your chips or something. Latches and flip-flops, there's a few places where you need to do timing, and so being able to, understanding what a D flip-flop is versus a JK flip-flop versus a T flip-flop versus an SR latch. So it's a little bit of knowledge you have to have, but understanding how those works is really important for knowing how to build one of these things. Some other stuff, you need registers. Sometimes you need shift registers. Usually it's parallel registers and counters. It's really helpful to be able to do things that count up, count down without needing the ALU involved. So implementing things as registers that have counting ability can be really helpful. And bus transceivers. I have more 74 245s in my design than basically any other chip because it's the gate that sits between some sort of register and your bus. It's a bus transceiver. So you're going to put a bunch of those in there, and then you're going to have a few special chips. And this is where being able to go to like the Wikipedia list of 7400 series chips is really handy. You search for like, I might need a priority encoder. And so you just search for priority encoder like, oh, there's like 10 of them I can choose from with all sorts of different attributes. Some of them have output enables, some don't. Some can be cleared, some don't. And so you can just pick one. And that's what they did back in the day. You would get this big catalog from Texas Instruments that was like this thick, and you just like page through it and you'd find the chips you wanted and order them. And so it's all done online now. It's pretty cool. You go to Mauser, you got a parametric search, you can just find the chip you're looking for, get HC or something, and you're good to go. There is some stuff in the Odyssey that isn't 7400 series. My EEPROMs, I mean, you would argue that's age appropriate. The AT28C is a very common EEPROM. And there's a bunch of them. I think we've got 6 or 8 of them in the design. So I use them in a real 70s or 80s design. Those would have been like $30 each, and people wouldn't have used them. But today they're like $7 each. So they're super cheap, and so I use them as basically as a PAL. I'm using a dual port RAM, which I don't know if they even existed back in the day, but this was awesome. If you're going to build something like this and you don't want it to be a toy, dual port RAM is amazing because it means the video card and the CPU can be asynchronous from each other. They don't have to be aware of what they're each doing because the CPU talks on the A side, the video card talks on the B side, and they'd never have to know about each other except that they're reading and writing the same addresses in memory. Fantastic. I was able to get one as a sample. I just actually emailed IDT and said, hi, I'm a hobbyist. Can I get a sample? And they sent me one for free. So that was pretty cool. Keyboard controller, I cheated, and I used an AT1085, which has more horsepower than the entire rest of the CPU combined, but it's doing keyboard service. I've got a Dallas RTC in there, which is, you can find those on old CPUs all the time, old computers, and I'm using an 80C52 UART, which is the UART that came with the 8086. So it's actually in a ceramic package and everything. It's the old, and it's a 1-bit UART. It's got a 1-bit buffer. And I chose it because the common one, the 16550, is a giant Hershey bar. It's like this giant 47-pin something monstrosity. And the 80C52 is small. It's only a 28-pin chip, so it fit better on the board. And if you're going to implement a UART, this is something that it took me far too long to figure out. Your UART can't talk serial RS-232. If you just hook it up directly to your serial port, you're going to burn up your chip and you might burn up your serial port. You need an interposer, which is the MAX 202, MAX 232. There's several of these. I use the MAX 202, but you have to convert your TTL signals to RS-232 signals. So if you're building one of these, remember that because it'll mess you up. I already burned up one of my chips because I didn't know that, and I got on Reddit and they're like, "Where's your MAX 232?" I'm like, "What?" I'm like, "Oh, I need to add one of those." And my extended RAM is also something you wouldn't have found in an old computer. It's an AS6C 4008, which is just a big 512K memory. All right, let's talk about the wire wrap construction process. So I chose wire wrap. That doesn't mean it's the best. Doesn't mean everyone should do wire wrap. I had some good reasons to use wire wrap. It looks like this. You can come by my booth and you can see it live. It is a sight to behold. But it's actually not as bad as it looks. Like you might look at this and be like, oh my God, there is no way you could debug this. Why on earth would you put yourself through this? But the pros did this. Like back in the 70s and 80s and 60s, like this was how you prototype stuff. So it wasn't wrong. And in production, yeah, for sure. Like at MIT, if you go to their museum, they built the Lisp machines back in the 70s. These were full-on awesome. They actually ran Lisp in hardware. The CPU's instruction set was Lisp. Amazing. All designed on wire wrap. These giant boards with just wire wrap all over the back of them, TTL chips all over the front. Fantastic stuff. So it does work. But why? Why wire wrap? Well, what most people do, especially if you're watching Ben Eater videos, which are amazing, and there's nothing wrong with breadboards, but they have very low component density and unreliable connections. So if you take a breadboard, you might be able to get like 5 chips across there, and then you start branching all your connections off of it, and you've taken up the size of an index card with just those 5 chips. But on a wire wrap board, those same 5 chips are just in one tiny little column, and so you can fit about 5 times more chips on the same square footage of your desk than you can with breadboards. Trying to design something like the Odyssey on breadboards, I'd have a breadboard layout as big as this table. It'd be ridiculous. Whereas with wire wrap, I could compress it down to a much smaller area. And then there's the unreliable connections. You take that giant breadboard thing and you try to move it from your kitchen table into the closet, and then the next weekend you bring it back out, and I guarantee 2 or 3 of those wires have pulled themselves up out of the little sockets, and you're going to spend an hour debugging that before you are able to use it again. So breadboards are great for prototyping small stuff, especially if you can fit it on one breadboard, but once you start adding multiple breadboards and you're trying to link things together, in my opinion, it's just not reliable enough to do a complex project like this. So printed circuit boards, right? PCBWay, one of the sponsors out here. $5, $5 PCBs. For the big ones, they're like $50. It's relatively cheap. It's impossibly cheap compared with what it used to be. And honestly, that's probably the best way to do it. Like if you really wanted to build something and you don't mind sitting in front of a computer screen and designing your entire computer in CAD and then sending off a CAD design to a shop and then waiting a few weeks and then your boards come back and then you solder them together and then test them, that's how the pros do it today. It's perfectly reasonable. That's how people prototype these days. But if something goes wrong, your repair complexity is pretty high because you're going to have to add bodge wires, you're going to start cutting traces. You can't just like remove a wire like you can with wire wrap or with a breadboard. And you have to do all your design up front, plus or minus however big your boards are. So if you design like a backplane and then you can put each module on the backplane, you might be able to reduce that design to your individual module. But for me personally, I much preferred the visceral, hands-on activity of pulling wires from point to point, testing it, checking to see if it worked, watching my design grow instead of just staring at a computer screen for a year, moving polygons around and then sending it off to a shop. So it's a personal thing. I probably chose the harder option. I should have used PCBs, but I thought it was more fun to use wire wrap. So what about wire wrap? Well, it is expensive. Those Augut wire wrap prototyping boards, they don't make them anymore, so you have to get new old stock or get used ones on eBay. Like each of the boards you see were about $100-something on eBay, which isn't bad, all things considered, but you'd spend that much on the number of breadboards you'd need. But it is expensive to get a big prototyping board like that up front. And another complexity is that the wiring is all on the bottom. So with a PCB, if you're doing surface mount, or with a breadboard, you're working at the top of your chip, so everything's correct. Your VCC is at the top right, your ground is at the bottom left, and everything matches what you see in the data sheet. On wire wrap board, you flip your board over, and now everything's mirrored. And so you have to have patience, and you have to understand that that's happening, and there are lots of tricks. Back in the day, they used these little cards that you would mount on your breadboard pins or your wire wrap pins that had numbers on them that were mirrored so that you could map your pins to the function. What I did is actually just, you can see at my booth, I've got everything just drawn out from the top side with all the pin numbers so that when it came time to wrap it all I had to do was say, A5 to D6 and D7 to B5, and I would just, I didn't know what I was wrapping necessarily. I was just connecting pins, net list, but I had done all the work on the top side. The other thing that's good about wire wrap that I didn't talk about is the design speed and the kind of debugging part. Breadboards are good up to about 1 megahertz or so, maybe not even that fast depending on how many you link together, but wire wrap boards have if you get these good ones that have a built-in ground plane, you can run those really fast. They have very low capacitance, and so you can actually run 10 something megahertz, and they work just fine, at least from the signal integrity. There's lots of other reasons you may not be able to go that fast. With PCBs, you can go hundreds of megahertz, depending on your design. But wire wrap boards are definitely going to let you go faster than you can on a breadboard. So, if you're going to do wire wrap, what do you need? Well, you need a prototyping board. The brand that I like is Auget. If you just get on eBay and search Auget wire wrapping board, you'll see a bunch of results. There are other brands as well. If you just search wire wrapping prototyping board or something, you'll find them. They're getting harder to find on eBay, but they're still out there. A lot of times you have to get one that's used, and you have to pull all the old wires off of it and then reuse it. You're going to need wire wrapping wire. Don't waste your time with anything but Kynar. It's just not worth it. You can get the cheap stuff. It's like a couple dollars cheaper that's got the PVC insulation. Don't bother with it. The Kynar is the best. It just works best with the wire wrapping. I don't know what it is about Kynar, but only use Kynar. You need a wrapping tool. You can get the guns, but I never got one. I just used the hand tool. So all those posts have been just hand wire wrapped with the wire wrapping tool. You're going to need a good pair of tweezers, and you're going to need some sort of magnifier because when you're down in those pins, that little forest of pins, you're going to need to be moving wires around. Sometimes your fingers, big old fat sausage fingers, can't get in there. So a good pair of tweezers is helpful. I'm using, most wire wrapping tools will come with a stripper, but if you don't like the stripper that it comes with, Jameco, Mauser, they all sell, and actually on Amazon, you can get handheld strippers like your home style strippers, but that have a 30 gauge stripper point. Yeah, you don't want to nick the wire, so you definitely want a stripper that has a positive stop that won't nick the wire. So it needs to, when it closes all the way down, you still need to see a 30 gauge size hole, otherwise you nick your wire.
Would it be possible to make your own prototyping board?
Yes, you can make your own prototyping boards. You can buy wire wrap sockets. So you can take perf board and you can buy wire wrap sockets. You actually still can get those new. You can also get wire wrap socket pins, like rows of pins, and just lay them on your board and then solder them from the bottom, and then you can just insert your chips wherever you want. And then a magnifier. So again, you're looking through this forest of pins. It's really nice to have a magnifying glass and a good set of reading glasses and a nice light that you can move around because otherwise you just get a headache and get tired. But yeah, good point about the, you don't have to use a prototyping board like this. In fact, the old school, if you look online at old images of old wire wrapping projects, it was very common that you would be building something, you just take just a plain brown proto board and then just insert the sockets you needed, and the sockets have these long, inch long pins instead of the really short ones. And then from the bottom, you would either solder the bottom to hold it in, or you just wrap a wire onto it to hold it in place, and then you would just wrap it all up that way. The prototyping boards are great because all the pins are already set. You've got a ground plane, you have a VCC plane, you've got sockets on the top and the bottom for things like decoupling capacitors. It's a much more comfortable way. I mean, and that's why they were expensive. They were used by the pros at these, IBM and stuff when they'd be designing these big computer peripherals because they needed hundreds of, wire wrapping posts. They weren't going to waste their time with a bunch of wire wrap sockets and stuff. They're just going to start plugging chips onto the board and start wire wrapping it from the back. So the technique that I use, again, you don't have to do it this way, but the technique I use is to start by sketching out a schematic. I'd often, for simple stuff, I would just literally write it in paper. I'd just draw some boxes and be like, all right, well, this needs to go there, and that needs to go there, and this OE needs to go to this control signal. But for the more complex stuff, especially when there's multiple layers of combinatorial logic, I'll use Logisim. There are lots of tools like Logisim. I just happen to really like it. It's very friendly. It's a Java program, but it can help you figure out, simulate your logic and make sure it's going to work. What I do is then I draw the prototype in. I draw the two columns that I'm going to put my chips in. I draw in where the chips are going to go and what the signal for each of those pins are. And then on the outside of those lines, I put in the actual net lists where they're going to go. You can come by my booth and see I've actually got the paperwork that I do this with. And then I write out a net list, which is just point to point, A2 to C5. D5 to B7, you know, just a bunch of list of connections that I need to make, flip the board over, wire the net list, connect, 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 then buzz the board, which is the term the old schoolers use, which is you just take a multimeter that's got a beeping feature and just go through your net list. My lovely wife here has helped me with that before, where she's reading out each of the items of the net list and beep, beep, beep. I'm testing each one to make sure I got it. And then test the functionality. So turn it on, see how it works, and inevitably there'll be one or two things you got wrong, either because you missed it in buzzing the board or because you just made a mistake in your logic, and so you can fix it. You can unwrap the wires, you can move things around, you can just cut a wire if you don't feel like removing it and just leave it in there and then wire a new one in place, and then fix as needed and then repeat for the next subsystem. So the whole idea, and I'm gonna get back to like you can do this yourself, is that you don't have to design the whole thing up front. You can do one little unit at a time, one column of chips at a time, and each time you finish with that column, you'll have added some functionality which you can then test and then make sure it works before you move on to the next step so that you don't feel overwhelmed. You don't end up with 1,000 wire wrap points and then you're wondering why this thing doesn't work and you don't even know where to start because you've built it up one little piece at a time. ADD just exploded. So that's it. Luckily, I was able to fit that into 40 minutes. Timing worked. I am going to be doing some demos, so feel free to come by my booth. You can't miss it. It's the Wire Wrap Odyssey, standing up straight. This is my website, which has way more information than I gave you here. 40 minutes is not long enough to do justice to everything that this project is, so all that's on my website. I'll be doing 2 demos at least. So today after lunch at 2 o'clock, I will be doing a logic analyzer demo. So I'll hook the logic analyzer up to the Odyssey computer and show everybody how I can like run a program and then basically like a breakpoint, I can trap a particular instruction or a particular memory address and then actually observe all these instructions and control signals that were happening before and after that breakpoint. Which was invaluable for being able to do this. So if you're going to build something like this yourself, you at least need a 16-channel logic analyzer. Even better, do what I did and get on Craigslist and get an old logic analyzer that has hundreds of signals, and that makes it so much easier because you can watch the memory bus, the address bus, your control signals, your instruction register, your program counter, your stack. You can watch it all simultaneously. You're not having to bounce around trying to debug your stuff one signal at a time. You can actually watch the entire state of the CPU every instruction.
It says one other plus point for wire wrap. Built-in probe points for every signal.
That's right. That is another good point. Is that if you're trying to test something, I can just take and put a probe right there on one of those pins, and you can go look at my design. I've actually a lot of these AuGet wire wrap boards have test points built into the board, so they have rows of just headers on the top of the board, and you can just run connectors from your design up to those probe points so that you're not having to deal with the octopus of 16 pins every time you want to debug. Instead, you can just take the pre-built 16-pin adapter and just drop it right onto that header. So I'm able to hook up all 190-something signals in a few seconds because it's just 6 dongles that I plug up to the top of the board, which is a lot easier. And if you're doing this on PCBs, you can do that as well, and I recommend it. If you're going to do a PCB, leave control point test points on there and make sure that they're compatible with your logic analyzer so you're not doing the octopus every time you hook up your analyzer.
Wire wrap is getting all those signals up there. You don't have to spend a lot of time thinking about how you get it from here to there on PCB.
Right, and yeah, that's a good point, is that when you're doing wire wrap, you're not routing because all your wires are insulated. So it's just point to point. So your wires can overlap, they can touch each other, they can overlap each other, and you don't have to worry about things shorting out. I'll do the demo again on Sunday. It looks like, based on the talk schedule, I'll probably do it somewhere around 11 a.m. If you're around on Sunday. And yeah, the Wire Wrap Odyssey. Any questions?
On your website, do you explain this as well, that the design from beginning to end?
Yes, so the website has all the information I showed here in 10 times more detail. So, and I will emphasize that while I do put all this information on my website, I never designed this to be reproducible. So if you're hoping like, oh, I'll go home and just do what Paul did. No, I mean, I did upload all my notes if you want to look through them, but they're literally paper notes. They've got like scribbles in the margins for like where I made mistakes and fixed them.
So we can make all those mistakes that you made?
Yeah, you can make all the same mistakes and then debug all those same mistakes. And I probably forgot to update some of those pages with the fixes I made. And so don't take those, what you can do is look through the notes and just see how I implemented something and maybe use it as inspiration, but don't treat it as a set of schematics you're going to use yourself.
I let him go.
Yes.
On the software side, what have you built? What is it doing right now?
Yeah, so that's a good question. On the software side, so all I talked about here was the hardware, but on the software side, that also evolved along with the hardware. So the first thing I had to do was actually had to write a compiler for my control signals. So basically implementing my instruction set. So something that took an 8-bit opcode, turned it into a sequence of micro-ops, and all that had to be compiled in a consistent manner into 4 32K control ROMs. And so I had to write a compiler first that did that would basically let me burn my control ROMs. And then once I did that, I used that same code and started bolting on an assembler to that so that I could write assembly code in my opcodes, and that would generate a sequence of programs. And that did, right now it does just very basic assembly. It doesn't even support like segments. It's just everything starts at 0 and just counts up. But it can do labels, and it's got some macro stuff built into it, so it's reasonably friendly to code in. And then with that foundation, I started building the operating system. So I put together essentially a BIOS. So I started building up a library of functions that do things like read from the keyboard, write to the terminal, scroll the display, set colors, talk to the clock, talk to the UART. And so I started building up this library of functions. I wrote a malloc function and a free function, and I wrote an sprintf function, and all these sort of things you needed as table stakes to just make useful software. And then once I started having those, I started writing the front-end software that basically used all that. So if you come by and look at it, you'll see it doesn't really do much interesting stuff yet. Like it'll print random numbers, or it'll print the date and time, or it can clear the screen, or it can calculate its own clock speed, or it can communicate over a serial port to a terminal. Kind of boring stuff, but it's all the stuff that it's doing under the hood that's interesting, and eventually it will do that other stuff. Eventually I'll write games for it, and I'll write VisiCalc or something, I don't know, but it'll be, there'll be interesting things that happen as I continue to evolve the system. But yeah, the software is where things go next. Yeah.
Thank you for a great talk. I have about 1,000 technical questions, and I can ask them all right now. I thought maybe, for one thing, I'm very impressed, and I think you probably felt like your own superhero while you were building this, I imagine, doing this for your own satisfaction. But there's a lot of other people out there that would be very impressed that you actually pulled it off, because I can only imagine thousands of hours that went into this. So I wonder if you can talk a little bit actually about what personally, how this affected you, both inspiration, challenges.
Yeah.
I think I'd have to sacrifice my personal and professional life for 5 years to pull this off.
So, thank you. And I think the most interesting thing that happened while I was working on this project was the connection that it built to the past. So I would be working on something because I didn't base this on an existing architecture. I didn't look at the 6502 and say, I'm going to build my own 6502 with TTL chips. I don't even know how the 6502 works inside. I don't know how the Z80 works inside. I know a bit about the 8088 because I used one, but I didn't base it on that. So I intentionally didn't over-research some of these things, and I just tried to kind of figure it out myself because that was more fun for me. But what I found was that almost every time I implemented something, I would get it working, and then later I would look at a YouTube video or I'd read an article, be like, oh, that's how the Apple did it. Or I would implement something else and say, oh, the ZX Spectrum did that. So I was actually unwittingly recreating a lot of these same discoveries and implementations that the original designers back in the 70s and 80s did, and I thought that was very cool. Probably the most telling version of that was when I was designing the video card. I designed the whole character generation logic on my own. Like I didn't even know that that's what, like I didn't know how character generation worked. I knew that it was a thing, but I didn't know how it worked. I didn't try to find out how it worked. I just did it. I figured it out myself, only to find that after I finished it and I started working on a font, I discovered int20h.org. I was like, oh, I can take these font ROMs that were downloaded from actual CGA, EGA, VGA cards, and they just work in my computer. Unmodified, which means I did it the same way they did without even knowing it. So that was very cool. And so, you know, from an inspiration perspective, that was, I think, the biggest takeaway is that this stuff, you know, the guys that did this back in the day were awesome in every respect because they built the foundation for the modern computing age we have today, but they also weren't magic. The stuff they did, all of us could do too. You can figure it out, like without needing someone to tell you how to do it, you can figure out how to do it, and they did too. So I thought that was very, very cool takeaway. Yeah, they didn't have Google, right? Right, yes.
Did you use 181 ALUs?
Good question.
And if you did, thoughts?
Yeah, so almost every wire-wrapped, TTL type computer of the day used the ubiquitous 74181 ALU. I was actually going to use the 74181. One, they're super hard to find. I don't know that anyone actually makes them anymore, so you can still get them. They have some clones on AliExpress you can get sometimes. I don't know if they would necessarily work. You can get new old stock. They're going to be all LS series logic, not CMOS logic, so it wasn't necessarily compatible with the logic series I was using. And when you look at the data sheet, the list of operations it can do the basics. It can add, subtract, increment, decrement, that kind of stuff. But of the 32 opcodes that it can do, like honestly, only about 5 of them are really useful. So I was like, well, that's a bunch of wasted bits. I could make my own ALU. I could use all 32 operations, and I could make all 32 operations do something useful. For example, I've got an ALU operation that explicitly knows how to set and clear the bits for blink and cursor in my video card. So instead of having to like write my own logic for that, I can run one ALU operation without having to like mess up another register and rewrite it that just says clear or set this bit or toggle that bit. So I decided to do it all on my own. And so I implemented it as a lookup table in an EEPROM because I had just done it with the control ROMs and it worked really well. So I wrote some Python code that basically wrote all the 32 operations I wanted it to do, and then just said, given these 15-bit inputs, this is what the expected outputs are, and then just wrote all that to ROM, and then wired that up as my ALU. All right, we got one more question.
Is there like a particular operation, either in the microcode or on the CPU, that you're particularly proud of that kind of maybe came together after all these other components were in place that kind of really made sense in the design and we're happy with it?
Good question. So 2 things. One was the way the interrupts work, because remember looking at the diagram, I implemented the interrupt hook way back at the beginning when I first designed the instruction sequencing, but I didn't actually know at the time how I was going to do interrupts. I just said, all right, when an interrupt comes in, I'm going to load instruction EE into the instruction register, and I don't know what I'm going to do after that, but that's how it's going to work. And then months, years went by, and then I went back to actually implement interrupts, and it worked, which was pretty cool. And so the fact that I had left myself room for 16 micro-ops for each opcode ended up being a savior there, because executing an interrupt requires a lot of moving data around and preparing the CPU so that when you can come back safely from the interrupt. And I needed actually 15 micro-ops to do that. So that ended up being a good architecture decision. The other one that I thought was interesting was I was observing that my scrolling performance, I would get to the bottom of the screen and hit enter, and it would scroll, like you could see it scrolling up. It was very slow. I didn't like it. I thought, well, it's microcode. I can just write new microcode. Well, it turned out that because I had up to 16 micro-ops per op, I could eliminate a bunch of the busy work the CPU was doing, bookkeeping, as it was rastering through the display, scrolling it up, by writing a single instruction, multiple data instruction. So I actually made some opcodes that are, move 4 bytes at a time instead of just 1. And so I improved the speed of the scroll by 5x, 10x. It was crazy. It went from like, you could see it scrolling to just instantly scrolling. And so I was able to do that without changing any wires. I just added a new opcode, reburned the control ROMs, and then just updated my scrolling code to use the SIMD instructions instead of the original ones. All right, I need to get off the stage for the next speaker, and I'm also in the way of your lunch. So thanks a lot, everybody. Appreciate it.